Hi, everyone. My name's Matthew. I'm a graduate student at Michigan State University, and I'm really excited to share work with you on developing genome annotations to enable phylogenetic inference on distributed digital evolution populations. I've been doing this work with my advisor, Dr. Charles Ofria, and collaborator, Dr. Emily Dolson. Phylogenetic analysis is a really critical part of evolutionary computing. It's important not only as a tool to investigate and understand evolutionary computing algorithms, but also as a tool to aid in tuning them so that we can get the best quality evolved solutions possible. Traditional phylogenetic work in evolutionary computing has depended on a perfect tracking model where each birth event and death event in the simulation are tracked and registered in a central database, something maybe like an analogy to a filing cabinet, where they're organized into a tree structure as they unfold, and this allows a record of exactly what happened in the simulation to be kept with perfect fidelity. However, scaling up this centralized perfect tracking model um, presents challenges. You could imagine kind of a centralized filing cabinet being a workable solution for a small group of people, but it starts to get to be a real slowdown and source of contention when you have much larger groups trying to use the same centralized data structure. And then when you introduce the possibility of lost data or corrupted data, the problems with this traditional model of perfect tracking become even larger. And so what we're pursuing in this work is a reconstruction-based approach to collecting phylogenetic information. This works kind of like you might be familiar with in traditional biology, where you have a set of extant organisms, maybe your set of solutions at the end of a run. You look at their genomes and you do comparisons between the extant organisms, and through some inference about the homologous similarities in these genomes, you can estimate the actual phylogenetic history of these extant organisms, how they're related to each other. And so in digital evolution, we control how genomes work. So our aim here is to design genomes to maximize phylogenetic reconstructability. And so I'll work you through our approach kind of by example, where these genomes are made up of growing sets of randomly generated fingerprints, where existing fingerprints are inherited from a parent, and then a new randomly generated piece of data is appended on the end. We'll run this out a few generations, grab some extant organisms, and compare them. And you can see where these line up, the fingerprints are the same, and that's where they have shared ancestry. And then we can identify exactly where the most recent common ancestor of these two extant organisms occurred. And so this is really intended as an annotation that can be added to any digital evolution system so that it can be used with great applicability and great generality. Uh, One problem you might anticipate here is the space complexity of this approach, and we address it by making a trade-off between the space that we use and the uncertainty that we're willing to introduce into our estimate of the generation window of the MRCA between two organisms by throwing out some of the fingerprints. And this is really the subtle and interesting part of this approach, which I'd be happy to discuss in the poster and take questions about, but I'm going to skip over it in the interest of time. With this approach, we've been able to estimate the MRCA within 10% relative error with 95% confidence, up to a trillion generations using really small genome annotations. And in doing actual tree reconstructions, we've been able to recover up to 85% of information for 5,000 generation lineages using only 64 bits of annotation. In future work, we're interested in extending to sexual populations because this is all assuming asexual populations. I'll credit the images, bibliography, acknowledge my co-authors and collaborators, and I'd be happy to take questions. Lots of materials available, including a software library.